This is the pre-lab talk for experiment number 8, Thermochemistry Part 1, for Chem 110 lab. The goals of this experiment are to measure the specific heat of several metals by analyzing heat transfer data. We'll also take a look at the relationship between the molar heat capacities of those metals. We'll also take a look at a few types of endothermic and exothermic processes, namely the dissolution of ionic compounds in water. Finally, but importantly, this experiment serves as an introduction to vernier sensors and the Logger Pro software. In today's safety pause, we focus on hot plate safety. It is important to make sure that you take care to not touch the surface of the hot plate once you begin heating. Another related topic to this is to make sure that the hot plate is completely turned off, that is, the heating is set to 0 before you plug it in. There have been many accidental burns, that is, that have occurred because students plugged in a hot plate that was set on a high heating. It is also important to make sure that you keep wiring away from the hot plates. This includes the plug for the hot plate itself and any wiring associated with the temperature sensor or the LabQuest Mini. And in some cases in our labs, the wiring that goes along with the mouse. Finally, it's important to let the hot plates cool down before putting them away in their respective cabinets. This is to not only prevent burns, but to prevent wiring from becoming damaged. And as always, we want to make sure that we goggle it and wear our flame-resistant lab coats. In this experiment, we get a chance to look at thermochemistry in action. Remember from lecture that thermochemistry is the study of heat exchange that occurs during chemical and physical processes. In this experiment, we'll be doing some calorimetry experiments, in particular for part 1. Calorimetry centers around the first law of thermodynamics. The first law of thermodynamics says that energy is always conserved during any chemical or physical process, which means that the energy in our universe, which is the sum of the energy for the system and energy for the surroundings, must always equal 0. In this equation on the slide, Q is the heat that's evolved from the system or surroundings. If we rearrange this equation, we see that this means that for any heat that is absorbed by the system, that heat must be evolved from the surroundings, and vice versa. We can use this relationship to help us calculate, for example, the specific heat of metal samples, which we'll be doing in part 1. To calculate Q for the system and the surroundings, which in part 1 would be our metal sample and our water, for example, we'll use the equation Q is equal to M times C times delta T, where M is the mass of the substance that's being heated, C is its specific heat capacity, and delta T is the change in temperature that substance undergoes. Remember, for calculating this delta T, we always take the final temperature and subtract the initial temperature from it. These equations will become pretty important for part 1 of this experiment. In part 2 of this experiment, we'll be looking at the dissolution of different salts in water and determining if that dissolving process is exothermic or endothermic. We will then compare our results to calculated enthalpy changes for those processes. We can calculate the enthalpy change for a reaction, which is related to the heat exchanged at constant pressure, by using standard enthalpies of formation. You can find these standard enthalpies of formation by looking at Table B in your lab assignment. To calculate delta H using these standard heats of formation, we take the sum of the heats of formation for our products and subtract the sum of the heats of formation for our reactants. Another important thing to remember is that we multiply each heat of formation by the number of moles of that substance that appears in the balanced chemical equation. Thus, it's important that we have a balanced equation before we start using standard enthalpies of formation to do our calculations. Another important aspect is that typically for reactions that occur in solution, such as the dissolution process that we're looking at here, or some single displacement reactions, which we'll calculate delta H for in the pre-lab assignment, you'll need to write a net ionic equation. Oftentimes, aqueous compounds do not have tabulated standard heats of formation. So net ionic equation is always going to be necessary. Another thing to remember as we're calculating delta H for our dissolving processes is that water does not appear as a reactant or product. Therefore, to write an equation for dissolving a salt in water, you simply just have the solid salt or ionic compound as your reactant and the aqueous ions as your product. For example, if you dissolve solid sodium chloride in water, you'll have sodium ions in aqueous solution and chloride ions in aqueous solution as your product. Let's look at some procedural points. As mentioned in the goals, this lab serves as an introduction to the vernier temperature sensor and LagerPro software. There's information about how to use the software and the sensor both in the procedure for the lab and also in Appendix C of the lab manual. The temperature sensor is a stainless steel rod that gets connected to a piece of equipment called a LabQuest Mini, which serves as the interface between the computer and the sensor itself. The LagerPro software allows us to collect temperature data either as a time-based measurement or as an events with entry measurement. We'll get to explore both of these options as we carry on with lab this term. But refer to the lab videos to look at how to use this equipment. In part one, we'll carry out the heating of our samples in the air capture units. This is mainly for safety and to control the temperature of the room. As you can see from the picture, our coffee cup calorimeter composes of two styrofoam cups that are nested together. A lid is also placed on top of those cups to minimize heat loss. Since the styrofoam cups are pretty light, there's a big hazard for tipping over the content and spilling out the contents of our calorimeter. Therefore, we'll be stabilizing the calorimeter by placing it in a 400 milliliter beaker. In part one of the experiment, we'll be heating up our metals by placing them in an 8-inch test tube. You'll see that the 8-inch test tube has a rubber grip on the top, so that someone can pick up that test tube without getting burned. We'll be using these test tubes, but also as an extra precaution, using a heat-resistant glove when handling the test tubes themselves. Although this is something that you might not see in the video, it's pretty important that we check the purity of our metal samples. During a regular term, the metal samples are used by many different classes and are returned to the bottles after use, which is pretty different from what we usually do in our experiments, where we dispose of waste appropriately. However, it is very important to make sure that the metals are not mixed with one another as we do the measurements, since this will change our results. A final note is on significant figures. Although for all labs that we do, we should always carry through the significant figures for our calculations, but you really want to especially be careful in this experiment. Especially since we're doing a combination of addition and subtraction, namely with the delta T measurement. Your delta T is actually going to be measured through two significant figures once you do the subtraction. Therefore, your final specific heat should also have two significant figures. Please be mindful of this when you're doing your calculations. Hope you enjoy the video.